So let's forge ahead today. We didn't have quite enough time to get through and do an example last time, so we had to cut things a little bit short. We'll go through and do an air standard cycle example today using variable specific heat. Get your feet wet, not your face, your feet wet, applying the principles that we learned last time to calculating efficiency, heat addition, various quantities for a air standard cycle, and then we'll move on to analyzing a very common air standard cycle, which is the Otto cycle. The Otto cycle is the approximation of the internal combustion engine that's probably in your car. So any spark ignition engine, any gasoline engine approximates an Otto cycle. So we're going to be talking about an Otto cycle and how to calculate its efficiency. We'll do a little derivation and determine the expression for the efficiency of an Otto cycle, assuming constant specific heat. So that's the plan for today. Okay, let's do an example here, an air standard cycle example that involves actual numbers. Forget graphical problems. Let's do an actual numerical problem here. We have air as the working fluid inside of a piston cylinder device, closed system, and the air executes the following processes. We have state 1 to state 2, adiabatic compression. So let's put ourselves in the pressure volume diagram somewhere. So let's say this is state 1 right here. So adiabatic compression, so that means no heat transfer. Adiabatic means no heat transfer, so we compress. I guess I should move a little bit further over. So we compress, volume goes down, pressure goes up. So here is adiabatic compression from state 1 to state 2. Then we have isochoric heat addition. Isochoric means constant volume, and then we add heat. When you add heat, the air gets hotter and pressure goes up. So isochoric, so we're adding heat in here. Q in, and we end up at a higher pressure at state number 3. Then 3 to 4, adiabatic expansion. So no heat transfer, we're just going to expand. Volume goes up, pressure goes down. Volume goes up, expansion, pressure goes down. And then 4 back to 1. Might have to adjust this point. 4 back to 1 is isobaric heat rejection. So constant pressure, heat rejection. I think I need to go out a little further here, because 4 to 1 is constant pressure. So there we go. There's state number 4, and we're going to be rejecting heat. Q out from 3 to 4. The process works in the clockwise direction. The boundary work is the area bound by the PV curve. That's not so interesting. Let's draw the TS. Well, I'll tell you what, we'll do the TS diagram as we move along. PV diagram tells us everything about the cycle as far as adiabatic, isobaric, isochoric, et cetera, okay? So what are we supposed to find here? We're supposed to find, given some temperatures and pressures at some states. Let's see, at state 1, the initial state, I have a pressure of 100 kPa and a temperature of 300 Kelvin. And at state 3, which is the peak pressure state, peak temperature too, we're going to find, 1800 degrees. So we go all the way up to 1800 degrees at state 3. Pressure P2, I'm given a pressure at state 2. So I got pressure P2 and I have pressure at P1. So I have these things, okay? What am I supposed to find? I'm supposed to find the heat transfer into my working fluid. That's 2 to 3. And the heat transfer out of my working fluid. That is 4 back to 1, Q4 back to 1. And then once I have the heat transfers, I need to find the total work, the cycle work, and then the efficiency, which is work divided by Qn. So once I have the cycle work and the heat addition, I can immediately calculate the efficiency for the cycle. Okay? That's what I'm supposed to find. That's what I'm supposed to find. So let's get started here. Analysis. Analysis. Well, first of all, I want to calculate the heat transfer in. Now, the heat transfer in occurs from state 2 to state 3. So process 2 to 3, process 2 to 3. And by the way, that process 2 to 3 is isochoric heat addition. So constant volume heat addition process. Let's write down the energy balance. Q, we don't have the mass for the air. So I think I'm going to write everything from now on a per unit mass basis. So instead of using capital Q and capital W and et cetera, I'm going to write everything on a per unit mass basis because I don't have the mass of the working fluid, but I'm not interested in total heat transfer or total work. I'm interested in heat transfers and works per unit mass. So I can do everything on a per unit mass basis in this problem. So let's see here, Q 2 to 3 minus the specific work 2 to 3 is equal to delta E 2 to 3. Now, the cycle analysis assumption says that the work is W is work boundary. So this is W bound from 2 to 3. If it's an isochoric process, 2 to 3, what's the boundary work? 0. It's isochoric. Constant volume, constant volume. So integral of PDV is 0. The heat transfer, of course, Q from 2 to 3 is the heat input. So this is Qn, which is what I want. Let's see here, no changes in kinetic and potential energy for our cycle analysis stuff. So delta E simply becomes a delta U from, 2 to 3. Why did I write 1 to 2? 2 to 3, 2 to 3, there we go. So delta E becomes a delta U because there's no change in kinetic and potential energy from state 2 to state 3. So we have a simple result. Q 2 to 3, or if you like Qn, is equal to delta U from 2 to 3, or if you like U3 minus U2. Now, U3, what is U3? Can I get U3? Well, I do have a temperature at state 3. I have the temperature up here at state 3. Okay? So I should be able to pull out going to, let's see, the temperature at state 3 is 1800 degrees. So I should be able to pull out from a table, share the screen here. Let's go to IGB air. This is not a constant specific heat problem. It doesn't say anything about constant specific heat. So I have to assume variable specific heat. Ideal gas properties for air, 1800 degrees. It looks like I have, it looks like I have 1487.2, 1487.2 kilojoule per kilogram. So that's U3. So 1487.2, 1487.2. So U3 is U evaluated at T3, which is 1800 or 14, sorry, I got to look it up again, 1487, is that what I said? 1487.2 kilojoules per kilogram. Okay. Okay, so I have U3. That's good. I got U3. Now, how do I get U2? Well, what is process 1 to 2? Let's have a look at process 1 to 2. Process 1 to 2. Adiabatic compression from state 1 to state 2. Process 1 to 2 is adiabatic compression. Let's see if we can get state 2 by what we know about process 1 to 2. So process 1 to 2, that is adiabatic compression. By the way, not only is it adiabatic, but it's reversible. Why? Because of cycle assumptions, air standard cycle assumptions. So it's also reversible, internally reversible. You might want to put the word internal right before reversible. Adiabatic and internally reversible. Let's write the entropy balance over the process. Closest entropy balance, delta S from 1 to 2. I guess I'll do it on a specific. 1 to 2 is equal to the integral of del Q over T from state 1 to state 2 plus S gen 1 to 2. It's internally reversible. Reversible inside. So that's 0. And it's adiabatic. So there's no heat transfer. So that means delta S is equal to 0. S2 is equal to S1. It's isentropic. Isentropic compression. If it's reversible, internally reversible, and it's adiabatic, it's isentropic. Okay? Now, what do I know about, what else do I know about state 2? So at state 1, I know the temperature and pressure. At state 2, I know the pressure. So I know the pressure change between 1 and 2. And I also know that it's isentropic. So I can write the following. PR2 over PR1 is equal to P2 over P1. For an isentropic process, I can write the ratio of reduced pressures is equal to the ratio of pressures. Okay? If I can find PR2, I can pull out an internal energy at state 2. So let's see here. PR2 is equal to PR1, P2 over P1. Now PR1 is equal to PR evaluated at T1, which is 300 degrees Kelvin. So I can get that from a table. Let's see if we can find it in the table here. So PR1 is PR at, so here's PR at a temperature T1, which is 300 degrees Kelvin, 1.386. 1.386. So PR1 is 1.386. .386. So I know PR1, PR2 and PR1 I know. So let's see here, 1.386 times P2 is 800 kPa. So I know the pressure here right at the end of my isentropic compression. So that's 800 kPa. And I know the initial pressure is 100. So I have 800 divided by 100. The kPa's cancel out. And I get 8 times. So I get 11.088. 11.088. So U2 is equal to U evaluated at a reduced pressure PR2, which is equal to 11.088. Let's find for the isentropic process, let's find the internal energy at PR 11.088. Let's see here. Here's PR. Remember it says for delta S equals 0. 11. Basically, it's right here. Here's 11 right here. That would tell me that internal energy is around 389.34 kilojoules per kilogram. If you do the exact interpolation, you get 389.22. 389.22. 389.22 kilojoules per kilogram. So now I have U3 and I have U2. Okay, let's see here. U3 is 114.87.2 minus 389.22, and that has units of kilojoules per kilogram. And I get a final heat transfer, Qin, of 1098 kilojoules per kilogram. A little bit of rounding there. 1098 kilojoule per kilogram. So maybe I should put up my TS diagram and start keeping track of some of these numbers here. So let's see here. We start off, and I'm going to label the heat transfers here. Let's see, we start off at state 1. So here's state 1. 1 to 2 is isentropic compression, so temperature goes up as I squeeze the air down. No heat transfer. And then from 2 to 3, I have some kind, it's constant volume. So volume is held constant, I'm adding heat. If volume is held constant, pressure must be going up. So here's pressure going up as I add heat. By the way, if you don't see this, the temperature must be going up from 2 to 3. So note from 2 to 3, let me write it right over here. Give myself a little bit of room. So note 2 to 3. Note volume is equal to constant. That means over the process, pressure divided by temperature at state 2 has got to be equal to pressure divided by temperature at state 3. Just write out the ideal gas law. Well, hell, let's just do that right now. Maybe I'm getting a little too far ahead here. So we have PV over MRT at state 2. And then we have PV over MRT at state 3. MRTs and the volumes cancel out. because it's isochoric. And so this implies that temperature T3, so let me put the temperature T3 over here and the temperature T2 over there. Temperature T3 is equal to P3 over P2 times T2. Pressure P3 is greater than P2. Pressure's going up as I add heat. It's getting hotter, so pressure has to go up. Pressure goes up, temperature T3 has to go up. Okay, so that's why I know that temperature increases from state 2 to state 3. So Qn, let's see here, Qn is 1098. 1098 kilojoule per kilogram. So this is state 3. Process 3 to 4 is adiabatic expansion. If it's adiabatic and reversible, what does 3 to 4 look like? Well, if it's adiabatic and reversible, therefore it's isentropic. So it's going to be isentropic expansion. Temperature will fall as it expands and cools down. And then 4 back to 1 is isobaric heat rejection. So we're going to go back to state 1. And this is where we reject heat, Q out. Okay? So there's the TS diagram right there. 2 isentropic processes, adiabatic and reversible, and 2 heat interactions going on. Okay, so there's our TS diagram. Q8 was 1098. Let's keep track of that. Let's keep track of that 1098. Okay? Now let's calculate the heat rejection, Q out. Let's calculate Q out. Let's calculate Q out. Process. The heat rejection occurs from 4 to 1. Heat rejection occurs from 4 to 1. And 4 to 1 is isobaric. Isobaric heat rejection, okay? So let's write the energy balance right here. So we have Q. Now, this is heat rejection out. So we have Q is equal to W times delta U. And this is all from 4 to 1, 4 to 1, 4 to 1. Now, the heat interaction from 4 to 1 is out of my system. So 4 to 1 is out of my system, out. So I need to put a negative Q out in the place of Q. So this is negative Q out. Why the negative sign? Because it is out of the system. That's why we have the negative sign. The boundary work. What's going on with the boundary work? This is an isobaric process. This is an isobaric process. So the integral of PDV, is equal to pressure times the change in specific volume. That's specific work. It's an isobaric process. I can pull the pressure out of the integral, and I get P delta V. Or if you like, P delta V from state 1 to state 2. It's an isobaric process. Okay, fine. Now what I'm going to do is I'm going to take the PDV and I'm going to put it on the right-hand side of the equation. And I get negative Q out is equal to delta U from 1 to 2 plus P delta V from 1 to 2. That's specific volume. Delta U plus P delta V, or if you like, delta PV, because it's constant pressure, delta PV from 1 to 2 gives me delta H. So Q out, Let's put the negative sign over on the other side. Q out is equal to negative delta H from 4 to 1, not 1 to 2. 4 to 1, 4 to 1, 4 to 1, 4 to 1. I don't know why I'm doing 1 to 2. Okay, delta H from 4 to 1, which is equal to H1 minus H4. Okay, H1 minus H4. H1 minus H4. Now, H1 I think I can get. H1 is equal to H evaluated T1, which is 300 degrees Kelvin. It's going to be about 300 kilojoules per kilogram. So H1, looking up in IGB tables, H1, 300.19 or so, 300.19 or so. So H1 is 300.19 kilojoule per kilogram. Okay, so I have H1 now. Halfway to getting Q out. Halfway to getting Q out. Okay, I need to get H4. I need to get H4 now. So H, the specific enthalpy at state 4. I need to get specific enthalpy at state 4. Well, what do I know about, let's look at the process from 3 to 4. I know it's an isentropic process. I know it's an isentropic process. Process 3 to 4. That's adiabatic and internally reversible. And int reversible. So we apply the S balance and we'll get isentropic. Isentropic. We'll get isentropic if we apply the entropy balance, okay? Now, if I can get a PR, if I can get a reduced pressure at state 4, I can get H4. If I can get a reduced pressure at state 4, I can get an H4. Okay? Now, how might I get a reduced pressure at state 4? Well, let's look at state 3 to 4. So we have PR 3 over PR4 is equal to P3 over P4. Now, what do I know about any of this? This is what I want. I actually want PR4. If I can get PR4, I can get H4. So PR4 is going to be equal to PR3 times, let's see here, P4 over P3, okay? Because it's an isentropic process. Now, do I know any of this? Do I know P4 or P3? Let's see here. Well, I actually know P4. Why? Because process 4 to 1 is isobaric. So P4 is equal to P1. P4 is equal to P1. Okay, I know P1. I also know PR3. PR3 is equal to PR evaluated at temperature T3, and temperature T3 is 1800 degrees Kelvin. We have temperature T3, the maximum temperature in the cycle. We have T3. that temperature, which is 1800 degrees. So I can get PR3. Let's see here, PR3 is 1310. 1310 from the table. 1310. From the tables, air tables. So I got PR3. And I got P1, which is P4. Okay? I don't have P3. I do not have P3. That's not good. How do I get P3? Well, let's look at the process. So I want to get the pressure at state 3. Let's look at the process 2 to 3 one more time. So I want to get this pressure here, P3. By the way, I know the pressure P2 is 800 kPa. But I want to somehow get the pressure at state 3. Somehow get the pressure at state 3. Let's see if we can figure out how to do that. Let's see here, process 2 to 3. Yes. This is isochoric heat addition. Heat addition. Isochoric means constant volume. Constant volume from 2 to 3, isochoric heat addition. Let's write out the ideal gas law. I'm interested in P3. Maybe I should write out the ideal gas law and see if this helps. Let's see here, equating the ideal gas law at state 2 and state 3. I have P2 V2 over T2 MR equals P3 over V3 T3 MR. Just equating the ideal gas laws, okay? Applied at the end states. Of course, the MRs cancel out. Now, this is an isochoric process, so V2 is equal to V3. And so I get P3 is equal to P2, T3 over T2. Now, I have P2, it's 800 kPa. I have T3, it's 1800 degrees Kelvin. I do not have P2, but I do know that process 1 to 2 is isentropic. Remember our whole analysis to get Qn? 1 to 2 is isentropic because it's adiabatic and internally reversible. Okay, so I can get T2. T2 is, starting to run out of room here. T2 is T evaluated at PR2, which we already calculated as 11,088. T2 was PR evaluated at 11,088. Let's have a look here. Let's see here, 11, okay, so it's basically right around 540 degrees. That's going to be T2. Do a little bit of interpolation here. I think it's just a little bit below. T2 is 539.8 degrees Kelvin. T2 is 539.8 degrees Kelvin. 539.82 degrees Kelvin. Okay, T2 I have. Let's see here, P2 is 800 kPa, and then I have T3, which is 1800, and I have T2, which is 539.8 degrees Kelvin. And I get a P3. Hopefully I have it cranked out here. I get a P3 of 2,668 kPa. 2,668 kPa. 2,668 kPa. Yep. Okay, now I can get PR4, so I can get H4. Let's see here. PR3, 13, 10. P4 is equal to P1, and that's 100 kPa. P3 is 2668 kPa, and I get a PR4. I get a PR4, reduced pressure at state 4 of 49.1. 49.1. So H4, God, I'm running out of room here. So H4 is equal to H evaluated at PR4, which is 49.1. And from IGB tables, I get 828.1 kilojoule per kilogram. 828.1 kilojoule per kilogram. Let's check that, all right? Let's go back to our IGB tables. So we have a PR4 of 49. Let's see if we can find it. 49, looks like it's around in here somewhere. Looks like about 820 something. 828 is what we have, okay? All right, I now have H4. Woof. And I have H1. Let's see here, H1 was 300.19 and H4 is 828. Oops, I forgot, let's see, did I get a sign error here? Let's see here, negative Q out. So I have negative delta H from 4 to 1. So this is going to be H4 minus H1, not H1 minus H4. Distribute the negative sign, okay? Delta H from 4 to 1 is H1 minus H4. Put a negative sign, I get H4 minus H1. This should be positive because it's Q out. Should be positive. Let's see here. H4 is 828 point something. 0.1 minus H1, which is 300.19, and all that has units of kilojoules per kilogram, and I get the heat output. Heat output is 527 kilojoules per kilogram. 527 kilojoules per kilogram. Running out of space here. Let's put it here. 527. 527. So this is 527 kilojoules per kilogram. 1,098 goes in. 527 goes out. What's the net work over the cycle? It's the difference between the two, Q in minus Q out. So let's calculate the net work. Let's calculate the net work. W cycle or net work. W cycle or net work equals Q for the cycle, or if you like Q net, or if you like Q in minus Q out. So I have 1098 minus 527, and that all has units of kilojoules per kilogram. And so let's see here, 1098 plus 527. And I get 571 kilojoules per kilogram. That's the net work or cycle work. W cycle, 571 kilojoules per kilogram. 571, okay? So let's put this on the TS diagram. The net work is the area bound by the TS curve. So I get W cycle is equal to 571 kilojoules per kilogram. Okay, that's the specific work for the cycle. Let's calculate the efficiency. Let's calculate the efficiency, eta. Let's calculate the efficiency, eta, for this cycle. Let's see here, efficiency for the cycle is equal to the work of the cycle divided by the heat input. I have all this stuff. Let's see here, 571 kilojoules per kilogram. The heat input was 1098. 98 kilojoules per kilogram. Those cancel out. And I get an efficiency. I get an efficiency of about 52%. It's like 51.9. So I'm going to write here 52%. 0.52, or if you like, 52%. So the efficiency of this cycle is 52%. Okay? Now, let's just take a moment here. We got just a few extra minutes. I might be going over a little bit, but I want to show you something. Let's say, so this cycle here has an efficiency of 52%. What if instead of having that cycle with its various processes, adiabatic compression, isochoric heat addition, adiabatic expansion, isobaric heat rejection, what if instead I put a Carnot cycle in there instead? And I put a Carnot cycle that operated between the highest temperature in the cycle, which is at T3, and the lowest temperature in the cycle, which is at T1. Let's calculate the Carnot efficiency for a device, a heat engine, operating between the two high and low temperature limits in cycle. Let's put Carnot heat engine operating between Tmax and Tmin limits. Let's do that. Let's put a Carnot heat engine operating. So now we have a Carnot heat engine operating between a maximum and a minimum temperature in my cycle. T high and T low, which is T max and T min. So what are the min and max temperatures in my cycle? The maximum temperature T3 is 1800 and the minimum T1 is 300. So I'm now going to take this old cycle and I'm going to stick a Carnot cycle in there instead. So now I have a T max equal 1800 degrees Kelvin, and I have a T min equals 300 degrees Kelvin. I'm going to take my old cycle that we've just been analyzing, and I'm going to calculate the efficiency of a Carnot heat engine operating between the same min and max temperature. Okay? Let's see here. So this thing is going to produce a certain amount of work over the cycle. It's going to receive a certain amount of heat Q high and reject a certain amount of heat Q low. The efficiency of the Carnot cycle, which by the way is the maximum efficiency in the cycle, is 1 minus T low over TH. Let's see here, what would that be? That would be 1 minus 300 over 1800 degrees Kelvin. 1 minus 300 over 1800. 1 minus 300 divided by 1800. 83%. 0.833, or eta max, eta Carnot, if you like. Eta max, eta Carnot is 83.3%. So if I analyzed a Carnot cycle between the same two temperature limits, 1800 degrees and 300 degrees, I would get 83%. Of course, the Carnot cycle has an efficiency that is a maximum, 83%, and that's greater than the efficiency of the cycle we actually analyzed. So you stick a Carnot cycle in place of any of these cycles that we analyze in this chapter, and you're going to get an efficiency greater than the efficiency of the cycle you've analyzed. The Carnot cycle is the most efficient. You stick a Carnot cycle in place of our cycle we've analyzed here with all its various processes, and you would get 83%, which is greater than the 52 that we calculated for our cycle. All right, ladies and gentlemen, I think that's all I want to say at the moment. We'll talk a little bit more about the Carnot efficiency a little bit later. Okay? All right, so let's have a look at the Otto cycle, which is a blackboard approximation for how the internal combustion engine works if you have a spark ignition engine or a gasoline engine. So the Otto cycle corresponds to a spark ignition, ignition engine. In other words, gasoline engine. So if you have a gasoline engine in your car, chances are you can approximately model the process, the cycle that goes on within the engine, within each cylinder in your engine. You can approximate that as an Otto cycle. So let's talk about the Otto cycle here. So let's put up a PV diagram, and then I'll put up a TS diagram afterwards. So here's a PV diagram, and here is a TS diagram. We'll do them both. Okay. So process. 1 to 2. Process 1 to 2. Let me make sure I start off in the right place. 1 to 2 is isentropic compression, or if you like, adiabatic compression. By the way, if it's adiabatic, you apply the entropy balance, assuming air standard cycle, of course, no irreversibilities within the piston cylinder device, within the system. If it's adiabatic, it also means that it's isentropic. So it's also isentropic compression. So here's state 1 right here. So up to state 2, isentropic compression. Temperature starts initially at T1 and goes up to T2. We're compressing, volume is declining, so temperature goes up. So here's state 2. In terms of the PV diagram, here's state 1. We are compressing it adiabatically, so pressure goes up. Pressure goes up as volume goes down. So here's state 2. By the way, this is volume V1, which is the maximum volume in our cycle. And V2 is the minimum volume in our cycle. You'll see that in just a moment. Okay? So 1 to 2, adiabatic or isentropic compression. Temperature goes up, volume goes down, pressure goes up. Okay? 2 to 3, instantaneous, instant combustion or heat release or burning of the air-fuel mixture inside the piston cylinder device results in an instantaneous, instant release of heat. The heat gets released so fast that the piston cylinder device isn't moving while all the heat is added. That means it's a constant volume heat addition process. Constant, or if you like, isochoric. Isochoric heat addition. So a spark occurs inside the piston cylinder device. The fuel burns very quickly, so quickly. But as far as the piston cylinder device is concerned, the heat is released instantaneously at constant volume. So if heat is released, temperature and pressure go up. So temperature and pressure go up. So we are adding heat Q in during the constant volume process. State 2 to state 3 is constant volume. And of course, temperature is going up and entropy is going up as well. Why is entropy going up from state 2 to state 3? Because entropy brings heat, brings in entropy with it. So we're adding heat, therefore we're adding entropy. Temperature and entropy increase. And then we end up at state 3. So Q in, okay? Q in 2 to 3. Q in 2 to 3. Then we have process 3 to 4, which is adiabatic expansion. If it's adiabatic, it means it's isentropic. Isentropic, so if it expands, temperature falls, pressure falls. So we have falling pressure, increasing volume, falling pressure, adiabatic, therefore isentropic to state 4. Isentropic expansion, temperature falls, no change in entropy because we have no heat transfer down to state 4, okay? Then to get back to state 1 to complete the cycle, 4 to 1, we have isentropic what? We have constant volume or isochoric heat rejection. Isochoric heat rejection. Isochoric heat rejection. Isochoric constant volume, Q out flows from 4 to 1. Temperature falls, entropy falls, heat transfers entropy out of the system because it's flowing out. It cools down and entropy falls. Okay, so this is a PV and TS diagram for the Otto cycle. The PV diagram is nice because it shows you the exact processes. The TS diagram is nice because it gives you an idea of work, cycle work, and efficiency, where the heat addition is occurring and where the heat rejection is occurring. Now let's actually calculate the theoretical efficiency for any Otto cycle. Let's calculate the efficiency for any Otto cycle. Efficiency of an Otto cycle. Let's do that. Now, first of all, let's define a quantity before we get started. I'm going to define a quantity R sub C. R sub C is called the compression ratio. Let me make sure let's get rid of the C. I'm going to be using that for something else. So let's call R is called the compression ratio. It's the ratio of the minimum to the maximum volume in the cycle. So let's go back and look here at the PV diagram. We have a minimum volume at V2 and a maximum volume at V1. And so the ratio of the two, we're calling that the compression ratio. That's going to be an important quantity here in just a moment. So let's make sure we define this. This is the compression ratio. We'll talk about that in just a minute as soon as we get to the actual expression for efficiency. Okay, so how do we calculate the efficiency of the Otto cycle? Well, the definition of efficiency, and this is for the Otto cycle now, the definition of efficiency is the work over the cycle divided by the heat input. Now, excuse me, I can rewrite this on a specific basis. So it's W cycle, lowercase, over lowercase qn, okay? Now the cycle work is equal to the difference between the heat transfer. So W cycle is actually Q in minus Q out. And of course, I'm dividing that by Q in. Okay? And you go through and you do a little bit of algebra here, very little. You get 1 minus Q out over Q in. Now let's figure out what these Q outs and Q ins are. By the way, before we get too much further here, we're going to assume constant specific heat for what we're doing to follow. So efficiency of an Otto cycle, and I'm going to put in parentheses here, constant Cp and Cv. So constant Cp, Cv, and therefore K. Okay? So the expression that we're going to derive for the efficiency of the Otto cycle is going to tell us exactly how efficient an Otto cycle is. It's going to be assuming constant specific heats. Okay? So let's figure out what Q out and Q in are. Let's see here. Q out occurs. So let's have a look at our PV and our TV diagrams. So Q out occurs from state 4 to 1, and Q in occurs from state 2 to 3. Q out, by the way, is out positive, and Q in is in positive. So we have to worry a little bit about the signs here. So Q out is 1 minus Q 4 to 1. And then I have Q in is Q 2 to 3. Why the minus sign in the parentheses? Because Q out is out positive. Q out is out positive from 4 to 1, whereas Q in is in positive 2 to 3. Remember, it's in positive in the energy balance, all right? Okay, so I need to figure out what these heat transfers are. If you like, I'll distribute the negative sign. 1 minus, no, I'll leave it. Let's just leave it. I will leave it exactly the way it is. Okay, so we need to find these heat transfers, Q2 to 3 and Q4 to 1. Let's look at process 2 to 3. If we go back and we look here on our Otto cycle, process 2 to 3 is constant isochoric heat addition. So constant volume heat addition. So process 2 to 3, isochoric heat addition, isochoric heat addition. Applying the energy balance, we have Q2 to 3 minus W2 to 3 is equal to delta U 2 to 3. And if we assume constant specific heats, that's going to be CV T3 minus T2. Okay, so that's Q2 to 3. Now, if it's an isochoric process, what's the boundary work? Remember, this is boundary work. So if it's an isochoric process, constant volume, what's the boundary work? It is 0. So this is 0 isochoric process. So we get immediately Q2 to 3 is equal to CV T3 minus T2. Okay? So I get 1 minus so CV T3 minus T2. Okay, so that's the denominator, that's the heat input. You go through and you calculate the heat rejection, you get the same thing. So process 4 to 1. So this is isochoric heat rejection. Okay, and I find that Q, or if you like, negative Q4 to 1 is equal to CV T4 minus T1. Okay, if you like. If you like. And that's out positive. Okay, so the numerator then is CV T4 minus T1. Okay? Now the CVs cancel out. And I get 1 minus T4 minus T1 over T3 minus T2. I got a bunch of temperatures in there related to the heat transfers in and out of my Otto cycle system, my system executing an Otto cycle. Let me do something that might look a little bit strange, but is actually very helpful. I'm going to divide the numerator. I'm going to extract out the T1 and the T2 from the numerator and the denominator, and I'm going to put them in front of the fraction. So I'm going to do 1 minus T1 over T2, extract out the T1 and the T2, and I have T4 over T1 minus 1 and T3 over T2 minus 1. Okay, that might look a little bit strange, but just bear with me for a second. Bear with me for a second. Let's look at the temperature ratio T4 over T1. Let's look at this process 4 to 1. Let's look one more time at process 4 to 1. Again, 4 to 1 is a constant volume heat addition, heat rejection. Constant volume heat rejection. Let's calculate delta S. Let's calculate delta S for process 4 to 1. Let's use a property relationship that involves those natural logs in there for constant specific heat. So delta S from 4 to 1 is CV. So let's look up our property relationships here for constant specific heat. Probably wondering where I'm getting this from. So let's have a look back at our property relationships here. Let's see here. So if you go look for that table, I think it's 6.2. I think it's page 155. No, let's see here. There we go. Delta S, constant specific heat. Here we go. I have a CV ln T final over T initial plus R ln V final over V initial, okay? So I have an expression here to get delta S, and it involves a change in volume. So let me write that down. So I have delta S from 4 to 1 is equal to CV ln T1 over T4 plus R ln V1 over V4. Okay? Now, this is an isochoric process, so V1 is equal to V4. So this ln of 1 is 0. And so I get delta S from 4 to 1 is equal to CV ln T1 over T4. Okay? Delta S 4 to 1. 4 to 1. I don't know why that says 4. Now, if you apply the entropy balance to process 3 to 2, if you apply the entropy balance, you apply the property relationship for process 3 to 2, you get a similar equation. You get delta S from 2 to 3 is equal to CV ln T3 over T2. Okay? Now let's go to our property, our TS diagram here. Notice that delta S from 2 to 3 is negative delta S from 4 to 1. 4 to 1, 2 to 3. They're opposite each other. So note, delta S 2 to 3 is negative delta S 4 to 1. So this guy is opposite, equal and opposite of this guy. So this implies these temperature ratios are equal and opposite in sign. I'm sorry, these temperature ratios are, be a little bit careful here. This implies T3 over T2 is equal to T4 over T1, since these delta S's are equal and opposite. Okay? T4 over T1 is equal to T3 over T2. That means this quantity in brackets is equal to 1, and it goes away. So I get 1 minus T1 over T2. I'm running out of space here. So I think what I'm going to do is I'm just going to dot, 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 dot. 1 minus T1 over T2. Okay? Now, what's T1 over T2? Let's look at process 1 to 2. Let's look at process 1 to 2. Process 1 to 2 is isentropic, adiabatic reversible, therefore isentropic compression. If it's isentropic, I can use a property relationship here. Let's have a look. So isentropic process for constant specific heats, IGB, isentropic process. So I have a T1 over a T2, which is equal to a V1 over a V2. Let me increase the, there we go. So if I have a T1 over a T2, that means V1 over V2, K, I'm sorry, 1 minus K. That's from the property relationship. That is from the property relationship. So this guy here is really V1 over V2, and then I have a 1 minus K. That's what that temperature ratio is in parentheses. Let me make sure that I have my, that looks good, 1 minus K. Now, I'm going to rewrite this ever so slightly differently. I'm going to take this ratio and put it in a denominator, in a fraction. So I'm going to have, so I get V1 over V2, 1 minus K. And I'm going to put this downstairs in a denominator. 1 minus 1 over V1 over V2, K minus 1. I just took the negative of the exponent and I get a K minus 1. Now, that quantity, V1 over V2, that's actually V max over V min. So let's go back and look at our PV diagram. V1 over V2. So you look at our PV diagram. Look at our PV diagram here. V1 is V max, V2 is V min. So I got the compression ratio down there in the denominator of my fraction. So this guy here is R, or the compression ratio. So I get 1 minus 1 over the compression ratio, K minus 1. So let's write this down here. The efficiency for a Otto cycle, assuming constant specific heats, is a function only of the compression ratio. 1 minus 1 over R, K minus 1. Put a box around that. Put a box around that. So the compression ratio is the only thing that dictates the efficiency of the Otto cycle. So as an engineer, a mechanical engineer, what does this tell you? If you want a very efficient Otto cycle, very efficient engine, so you want to increase efficiency. What do? You have to increase the compression ratio. So you want to increase the compression ratio, or if you like, maximize the difference between Vmin and Vmax. Okay? You want to increase the compression ratio, which is the ratio Vmax over Vmin. Now, for those of you that are motorheads, most gasoline engines, so gasoline engines typically have a compression ratio on the order of around 10, okay? On the order of around 10. The range, older cars are probably around 8, sometimes they're as low. Very old cars from the, around the war, the Second World War, maybe 6. Compression ratios have been going up. High performance engines that can run on a high octane fuel. High octane fuel is better for high compression ratio engines. High octane fuel, high compression engines, compression ratio engines, about 12 or so. Okay, it tops out at about 11 or 12. Now you might ask yourself, why are we stuck at around 10, 11, 12 for a compression ratio? Well, note, as R, the compression ratio goes up, you get what's called pinging or pre-detonation. You tend to get what's called pinging or pre-detonation. Pre-detonation. So it's basically uncontrolled burning of the fuel. If the fuel does not burn nice and smoothly, if it ignites at various locations all at the same time in the combustion chamber, so let's say you've got, so here's our combustion chamber right here. And here's our piston. And we're all the way up at top dead center, or near to top dead center, and you have air, fuel inside. If the air-fuel mixture starts to burn or release heat or explode, if you like, in multiple places, so you've got a flame here, you've got a flame there, you've got flames just spontaneously starting to burn before the spark plug ignites the fuel. Pre-detonation. Then these flames grow and they hit each other. The flame fronts hit each other and produce very large pressure spikes. So if you get pinging and pre-detonation, you get large pressure spikes in cylinder. And those pressure spikes, actually you can hear them, called pinging. The engine will make a ringing sound or a knocking sound. So you get large pressure spikes in the cylinder, and that will do damage to the engine, mechanical damage. So for those of you that think, well, why don't we just keep raising the compression ratio beyond 10 and get efficiencies as high as we like, there are mechanical and engineering reasons why we have not moved much beyond a compression ratio of 10. Direct injection, fuel injection, gasoline engines have helped that a little bit, but we're still stuck at around 10, 11, 12 for a compression ratio for most gasoline engines. Okay? Anyway, I hope this has been interesting. We will move on next time and talk about the diesel cycle, which is another cycle commonly used. And then we will move on to open systems, and look at gas turbines, for example. That will be for next time. Take care, ladies and gentlemen.